Hello everyone, my name is Saurabh Roy. I'm a PhD student in University of Florida under the supervision of Dr. Dominic Forte. Today I'm going to talk about self-timed sensors for detecting static optical side channel attacks. This is the outline of my talk. At first, I'll talk about optical side channel attacks. Then, specially, I'll focus on laser logic state imaging or LLSI attack, including its attack model, existing countermeasures, and our proposed countermeasure. And as a part of our proposed countermeasure, I will go in detail on clock freeze detection sensor and voltage modulation detection sensor. After that, I'll describe the results and I will end by talking about an overview, summary, and future work. Among the side channel attacks, there are timing, electromagnetic emanation, power analysis, FIB-based probing, and optical probing attacks. Among these side channel attacks, timing, electromagnetic emanation, and power analysis attacks are non-invasive attacks, and they are not so costly at the same time. But for these attacks, a lot of traces have to be taken in order to extract the secret information from a chip. In recent times, FIB-based probing and optical probing has become more popular, although FIB-based probing and optical probing machineries can be very expensive. But it gives attacker high capabilities of extracting secret information from a chip. Field-based probing is an electrical probing method which is mainly used for failure analysis techniques. Optical probing is also originally a failure analysis technique. But field-based probing can be destructive and uh, it can have high resolution. But optical probing can be done with high resolution, but at the same time in a non-invasive way. Among failure analysis techniques, there are photon emission analysis, thermal laser stimulation, and optical probing. In optical probing, electro-optic probing or EOP and electro-optic frequency mapping or EOFM can be used to obtain the dynamic characteristics of a transistor if the operating frequency of the transistor is known. But if the attacker wants to get the static signals of the transistors, EOP or UFM will not work. In that case, the attacker has to use laser logic state imaging or LLSI. It makes LLSI one of the most powerful FA techniques which can be used as an side channel attack. Let us talk about laser logic state imaging as a side channel attack. Recently, one of the most effective countermeasures against side channel attack is known to be masking scheme. In masking scheme, randomness is generated and it is assumed that the attacker has a limited number of probes at his or her disposal. But with LLSI, this very powerful masking scheme can also be broken because LLSI provides the attacker an unlimited number of contactless probes, which actually invalidates the assumption for the masking scheme that the attacker has a limited number of probes. Not only that, LLSI does not require any repeated measurements. As a result, the randomness in the masking scheme, it does not provide any protective effect. Here in the figure, we see the difference between classical UFM and LLSI. In classical UFM, the transistors which are switching as a data-dependent frequency can be found out. But the transistors which have static signals are not visible in this method. So if the attacker wants to know the static signals at a certain clock cycle, attacker can use LLSI. With LLSI, the static information of the transistors which are on can be obtained. So among the optical side channel attacks, laser logic state imaging can provide the attacker with a very high and effective capability to extract secret information. Now let us talk about the attack model of LLSI attack. Let us consider a device under test. So in order to get the static signals or the states of the transistors, attacker first freezes the system clock at a clock cycle of interest. After the clock is frozen, the attacker modulates the supply voltage at a known frequency. After clock freeze and supply voltage modulation is done, uh, attacker does laser scanning and gets the images of the key registers. From the LLSI image, attacker can find out which transistors are on, and from there attacker can extract sensitive information, security critical information such as key or assets. If we consider an SRAM cell, this is the LLSI image, simplified LLSI image of an SRAM cell. So from the LLSI image, it is possible to know which transistors are on. So if we know which transistors are on in an SRAM cell, we actually know what value is stored in that SRAM cell. So in this way, through LLSI attack, attacker can find out the key values stored in the memory at interested clock cycle and thus break the security of any chip. So the existing countermeasures of LLSI are LED-based photon detector and nanopyramid structures. In LED-based photon detector, an optically active layer is deposited at the chip backside, and if during LLSI and sample preparation, if the layer is damaged, it can be detected by the photo detector. So it can actually detect thinning of that optically active layer, and thus it can detect LLSI attack or other optical probing attack is happening. The problem is that it requires extra protective optical layer, which requires additional verification and fabrication steps. So another countermeasure is nanopyramid structures, which do not require any extra area and is passive by nature. And it works by scattering the laser that is incident on the chip, and it includes a randomness so that the detected beam do not actually provide any information to the attacker. But this also requires extra fabrication steps for the nanopyramids. As we see that there are two critical attack surfaces for LLSI attack, one is freezing the system clock and another is modulating the supply voltage, we propose a sensor that will detect the clock freeze and that will detect the voltage modulation. So our approach is a circuit-based one, which will not require extra fabrication steps and extra verification steps. Let us talk about clock freeze detection sensor. Here, this is the architectural diagram of the clock freeze detection sensor. This is an asynchronous sensor. That means that we need to generate our own sensor clock. Here we have a counter that counts the system clock pulses. And we have two registers, register 1 and register 2, that store the count values at sensor clock edges. We have a comparator that compared the consecutive register values from register 1 and register 2. We also have an FSM that check comparator output for about 5 clock cycles. Under normal operation, the count value changes with each system clock cycle, and the comparator output shows that the register 1 and register 2 values are not equal. But when clock freeze occurs, count value gets stuck at a certain value and register 1 and register 2 both have the same value. So the comparator shows that register 1 and register 2 have the same value, and the FSM makes sure that it stays at the same value for a certain sensor clock cycle and then raises the alarm. One important component of clock freeze detection sensor is the sensor clock generation circuit. Here, the sensor clock generation circuit is nothing but a ring oscillator that has n number of uh, inverters where n is odd. This sensor clock is generated internally and cannot be accessed by the attacker. Here we use two D flip-flops and an XOR gate to reduce the noise in the sensor clock output. Now let us talk about the result of clock freeze detection sensor. Here, from the simulation, we see that on top there is a system clock, and system clock is frozen at certain period. And the lower one is our sensor clock. So once the system clock is frozen, the counter value gets stuck. And register 1 and register 2, they both have the same value. So then FSM checks whether register 1 and register 2 values are the same for certain clock cycles. In this case, 5 clock cycles. 1, 2, 3, 4, 5. So after 5 clock cycle, if FSM still sees that register 1 and register 2 values are equal, then it raises the flag. And the flag is kept risen until the system clock is unfrozen again. So if the system clock is unfrozen again, register 1 and register 2 values are different, and the flag value goes down. Again, if the system clock is frozen again, the flag also goes up after 5 sensor clock cycles. So after the clock freeze detection sensor, let us talk about voltage modulation detection sensor. So as during LLSI attack, the supply voltage is modulated, we need a constant power supply. So in order to provide that constant power supply, we use an LDO that will generate the constant power supply for the frequency to voltage converter, the amplifier, and the comparator circuits. We also need some control signals for the frequency to voltage converter or FVC circuit. So we use a high pass filter and an amplifier to generate the control signals. So the frequency to voltage converter or FVC circuit output depends on the presence of modulation in the supply line. If there is no modulation, the FVC output remains at a constant value. But if there is a modulation, the output of FVC goes down and below a certain threshold. So we use a Schmidt trigger comparator to check whether the FVC output went below that threshold or not. If it goes below the threshold, that means there is a modulation in supply line and flag is raised by the Schmidt trigger comparator. This is the LDO circuit for FVC. LDO circuit takes the moderated supply voltage V in as input and produces a constant power supply V naught, which is used for FVC, the comparator circuit, and the amplifier circuit. So this is the control signal generator circuit for FVC, where high pass filter is used to filter out the constant DC voltage so that we only take the modulation. For simulation purposes, we used 170 millivolt peak to peak, and we found out that this circuit can actually detect modulation much lower than that. So the control and control B signals are used for the. This is the FVC circuit. FVC circuit is powered by a constant power supply V naught, which is supplied by the LDO. It is also controlled by two control signals, control and control B, which are supplied by control signal generator circuit. Control B is a 180-degree phase shifted version of control, and both of them has same frequency as the supply voltage modulation that we are going to detect. So there are one charging cycle and one discharging cycle, where the charging cycle occurs when control is low and control B is high, and discharging cycle occurs when control is high and control B is low. Through this charging and discharging cycle, um, the output of FVC V out, which is the voltage across capacitor C2, it settles down at a voltage which is lower than a certain threshold of about 390 millivolt. We use a Schmidt trigger comparator that detects the output voltage of FVC V out, and it raises a flag as soon as V out decreases and goes below a certain threshold of 390 millivolt. The flag stays risen as long as V out is below a voltage which is much higher than 390 millivolt, of about 700 millivolt. That means Schmidt trigger works in a hysteresis loop that increases the detection reliability of the voltage modulation sensor. Now let us talk about the results of voltage modulation detection sensor. Here, uh, the green curve is the output of FVC and the pink curve is the flag, so the output of the comparator. So at the absence of modulation, output of FVC does not change and the flag stays at 0. So once there is modulation in the supply line, the output of FVC goes down a certain threshold, and if a Schmidt trigger comparator detects it, the flag is risen from 0 to 1. It happens for frequencies of 90 kilohertz, 150 kilohertz, and 500 kilohertz as well. We selected these frequencies because previously in literature we found out that LLSI attack was successfully conducted at these frequencies. So both sensors can be used together to detect with higher accuracy, or either sensor can be used to detect either clock freeze or voltage modulation. So in summary, LLSI is a powerful side channel attack, and which gives attacker access to unlimited probes, and our proposed sensor can detect LLSI with high confidence according to our simulation. And in future, we want to investigate the effect of process and temperature variation on our sensor. We want to reduce the overhead of our sensor and also obtain silicon results. This work was sponsored in part by NSF and by US government. Thank you very much for listening to my presentation. If you have any question, I am available to answer those questions now. Thank you.